This lecture introduces the image and kernel of a linear transformation. So if you let L be a linear transformation that transforms some vectors in vector space V to a vector space W, then the kernel and image are the two subsets of V on which the linear transformation L has some special effect on the subspaces of V. Okay. Well, let's talk about the definitions of kernel and image. All right. So again, L is a linear transformation from V to W. Then the kernel of L, denoted KERL, and is defined as are the vectors in V, such that if you apply these linear transformations on those vectors, it will give you a zero vector in W. So what it does is to take subset of vectors of V and it's transformed to, so this is V, this is W, for example, right? And it takes some vectors in V, and if you use the linear transformations on these vectors, all of this will go to a zero vector in W. Okay, a set of just zero vector. All right, so that's the definition of the kernel of L. So this section here, this subset here is a kernel of L. Now, what is the definition of image? Again, you have a linear transformations and S to be a subspace of V. The image of S, denoted by LS, is defined by are the vectors, some of the vectors in W, such that there exists a vectors in V, V in V, so then W equals to L of V. Okay. What does it tell you? It tells you that if you have, here we go again, have V, and this is W. So W is the a subset of W, right? So that there exists for each of the vector in this set right here. This exists like, let's say, W, okay? And this exists a vector V in V such that LV equals to W. So if you pick any vector in this image, you always can find a vector in V, so then you can map this vector V to a vector in the image. So again, a kernel is a set of vectors in V, and the image is a set of vectors in W. Keep it in mind. When you think about functions, the kernel is just like the domain, and the image is like the range of a function. Okay. Well, let's look at example number 5. So you have a linear operator on R2. So that means you're sending, this is the linear transformation just from R2 to R2, linear operator. And this is the definitions of the linear operator. If you apply a vectors in R2, it will give you a vector where the second coordinate is 0 and it reserves the first coordinate. For example, if x is equals to x1 and x2, right, is a random vector in R2, then when you apply L on this x vector, you will get x1, which is the same, and x1 and x2 will goes to 0. So this is how you describe these linear transformations. Then the question is, can you find the kernel of L and the range or the image of L, right? The range of L. So if the image of the entire vector space LV is called the range of L. If you just look at a subset of W, then it's called an image. But if you look at the image of the entire vector space, then it is called the range of L. All right. So kernel. In order to find the kernel of L, you want to identify a generic vector that is in the kernel of L, and then you generalize the entire subspace or subset. So if you let V or X is a vector in the kernel of L, then by the definitions, Lx equals to 0 vector. Okay, so this is the definition of the kernel. And also by the definitions of the image, Lx equals to x1, 0. So if you want to rewrite this 0, you can just rewrite it as 0, 0, because it's a 0 vector. And if you want to be more specific about the x, you should have x is x1 and x2. Okay. Now this is the fact that x is in the kernel. And this is just the descriptions of the linear transformation that we're given, right? So by these two facts, this implies that, 0 is 0 equals to x1, 0 out of x. So that implies x1 equals to 0. And x2, that's the only conditions. And x2 can be any value. Okay. So when you generalize the this x vector, it's gonna be, so the condition for x is 0, and there's no condition for x2, so that means x2 can be any value, right? Where x2 is in R, and this is the kernel of L. So the kernel of L includes vectors whose first coordinate is 0 and second coordinate can be anything. Then if I want to rewrite this as a span, so it's going to be the span of the vector E2, which is 1, 0. Okay. It is a span of, this should be 0, 1. 0, 1, and 0, 1 here is actually the a unit vector of R2. Okay, or you can rewrite it as span of E2. Okay. What is the span of E2? You can try to visualize this. E2 is the vectors on the y-axis. So this vectors here, if you want to visualize it, there will be, so this is E2 right here. Span of E2 is all the combinations, linear combinations of E2, which means it consists of all the vectors on the y-axis here. Okay. So this is the span of E2, which is a line y-axis. And this is actually the kernel of L. How about the image or the range? So the range of L is just the image of all vector space. Okay. Again, we want to call out an arbitrary vector y in R2, and I want to specify y1, y2. And this is in the range of L. Okay. So if y is the range of L, by the definitions, there exists a vector x, okay, in R2 such that Lx equals to y. So I can rewrite x as x1, x2. Okay. So that's one thing that we know. And another thing that we know is we can always use the descriptions of the map also. Lx equals to x1, 0. Okay. That implies that L x1, x2 equals to y1, y2 equals to x1, 0. This implies that y2 has to be equals to 0. And y1 can be anything, because x1 here can be any value, right? So this tells us generalize the kernel of the range of L equals to a set of vectors y of 0 and this should be y1 and 0. Okay, such that this is in R2, such that L of x equals to y for some x in R2. Okay, and if you want to rewrite this as a span of a set of vectors, so it's going to be the span of 1, 0, and which is the same as span of E1. So the range of L is a span of E1. And what is E1? E1 is a unit vector in R2. It's xy. And you can see that this is E1 right here. And the span of E1, just all the linear combinations of E1. So it's just all the vectors that are on the x-axis, which is a span right here. And remember the kernel that we found earlier is a span of E2. So which is all the vectors on the y-axis. So this is the idea of how we can find the kernel of a linear transformations and the range of linear transformations, right? To find the kernel, you want to set a vector x in the kernel. And then by the definition of the kernel, Lx has to be equal to 0. And by the definitions of the linear transformation, Lx equals to x1 equal to 0. And then from these two informations, these two pieces, you can force them equal to each other, and you can find some condition for a vector to be in the kernel. So the condition is x1 equals to 0 has to be equal to 0, and x2 can be anything. So from these conditions, you can generalize the kernel of in linear transformations by taking all the vectors whose x1 equals to 0 and x2 can be anything, any value, to be the kernel, and then you can translate this set into different descriptions of a set, which is using the span of the set of vector. And you can see that this is the span of 0, 1. And 0, 1 it actually is E2, one of the unit vector. And then you can visualize this using the XY coordinate. Similarly, to find the range of a linear transformation, you call out a generic or an arbitrary vector in the range. By the definitions, you will have to come up with one vector, right, x, such that Lx equals to y. And then also using the linear transformation description, you know that Lx equals to x1, 0. So then you can figure some conditions for this vector y. And in this case, the conditions, there's only conditions for vector y is y2 has to be 0 and y1 can be anything, because y2 is 0 and y1 is just x1, which is the real value, right? If y2 equals 0, then you can generalize the range of L by collecting all the vectors whose y2 equals to 0 and y1 can be anything. So it should be this, and this set here is the same as the span of 1, 0, and which is E1. And E1, the span of E1 is just the collection of all the vectors in all the vectors on the x-axis. All right, so this is the definitions and an example of a kernel and an image of a linear transformations.